Our shout out, we have a lot of people gone today, but in particular Whitney, she's a little bit of pain. She just had her wisdom teeth out. We want to say hi to Whitney?
Oh. Hi, Whitney.
Whitney, I just have to say I really enjoyed your Be Real the other day.
Whitney, I know your pain and I'm so sorry.
Whitney, have some ice cream. Right? Ice cream, popsicles, whatever. I think she's going to show up. Okay, bye, Laura.
Good luck, Laura. We love you.
Okay, so we need to start looking at the applications of the integral. The integral is it's a pretty cool thing. We talked about just three things that you need to be able to do in calculus. One are limits, one are derivatives, and then one is integrals. The test that you just had a test on, that was the test on integrals. So if that didn't go the best for you, that's one you want to relook at. We can sit down together, spend some good math time, figure it out. So this is the application of the integrals, and one application is finding the area between two curves. So instead of finding the area underneath the curve, we want to find the area bounded, say from A to B of this region right there. And that may look challenging, but it's really not that bad. For example, if I were to examine just a small sliver of it, remember when we used to draw rectangles? We used to draw rectangles, and we used to find the area of all of these rectangles. We actually say that the width of this rectangle is dx. dx. Infinitely small. Okay, we said the width is dx. And then we want to consider the height. Suppose that the height of this red line right there, suppose it was 10, and suppose the height of the blue was 7. What would then be the height of the rectangle? 3. You took the top minus the bottom. And so 10 minus 7 gave me that 3. Okay? And so if you want to find the height of the rectangle, so that one rectangle has these dimensions. The width is dx, and then the height is simply f of x minus g of x. And how is it that we find the area of a rectangle? You take the base times the height, right? So if we want to write a formula for area bounded between two curves, we take the height, which is f of x minus g of x. We multiply by the width, which is dx. That is simply one rectangle. I don't want to do one rectangle. How many do I want to do? An infinite number of them. The way that we move from one rectangle to an infinite number is we slap on an integral symbol, and we go from A to B. We good, Kaylee? Okay. So, we're going to look at the area bounded between x squared and y equals negative 2x plus 3. We're going to look at the interval from 0 to 1. And what's really important is for you to identify what the picture looks like so that you know which one is on top and which one's on bottom. So what does the graph of x squared look like? It's a parabola that is centered at 0, 0. What does the graph of y equals negative 2x plus 3 look like? It's a line, goes through 3 and has a slope of Negative 2, so it looks something like that. So I'm looking at the area, and it's very important that you recognize, the graphical relationship here. Notice that if I'm over here, is the line on top or bottom? The line's on bottom, but if I'm right here, the line's on top. And notice I'm going from 0 to 1, so I'm kind of looking for area around that region. So once you discover the area you're looking for, you can say, well, the top is negative 2x plus 3, and the bottom is x squared. So the integral is simply the top, which is negative 2x plus 3, minus the bottom, minus x squared. So that's the height of one of those rectangles. The width is dx. And we integrate from what to what? 0 to 1. Now the challenging thing about this unit, I think for me at least, is there's no way to really check that you set up the integral correctly. There's really no way to check that. It's just careful precision that you have to go through to make sure that's set up correctly. After this, it's all easy. We know how to evaluate that, don't we? Yeah, you just take the antiderivative. Antiderivative of negative 2x, negative x squared. Antiderivative of 3, 3x minus x cubed over 3. That's going to be evaluated at 1 and at 0. What's really nice in this situation is if you plug in 0, you get 0. If you plug in 1, you get negative 1 plus 3 minus 1/3. So I get positive 2 minus 1/3. I'm going to write it as 6/3 minus 1/3 is 5/3. Your calculator, if you plug this in, it will evaluate that, but your calculator will not say graph both functions and I'll try to find the area between it. It doesn't do that. So you can check to make sure that your your arithmetic comes out correctly, but whether or not that's set up correctly, there's really no way. You have to see it. Okay? Nope. You plug in the thingy. Yep. Okay. All right. Example 2. This is we're gonna so these do get slightly a little bit more challenging, not a lot, but please really pay attention as we talk about this one. Okay. Area between the curves y equals x squared minus 2x plus 1 and y equals 2x plus 1. Talk to your peer. Just looking at it, how is this one different than the one up above? There's something that should stand out immediately. Talk. Go. Okay, 5, 4, 3, 2, 1. What's missing in this problem? The intervals are missing. So we're going to have to determine the intervals. By the way, this section, as we're discovering area, we're actually going to then turn to volume, which is super cool. But this is the second most commonly asked question on the AP exam. Okay, so when you get to your free response section, this is one that will most likely come up that we want to be really good at. So let's first look at the graphs. X squared minus 2x plus 1, what does that look like? A parabola, do you recognize that it factors to x minus 1 times x minus 1? Yeah. So therefore, it's a parabola that has a vertex sitting here at 1. It has this shape. The sketch doesn't have to be perfect. The next one is a line. We can see it crosses at 1 and it has a slope of 2. Before I go to the bounds, because we all know that that's an issue, what I'd like to do first is I would like to look at the rectangle that I draw from the top to the bottom. So notice I have the top and I have the bottom. Now I'm going to use a different term, this width of the rectangle. Everybody make sure you watch this because this will change. Is this horizontal width or is it vertical width? The width of the rectangle, is it horizontal or is it vertical? It's a horizontal width. If I drew the rectangle like this, now is the width horizontal or vertical? See the difference? If it's horizontal width, we say it's dx. If it's vertical width, we say it's dy. So the most important thing you establish right away when you're doing these is, do you have a width of dx or dy? We all good with dx? Good. That tells us that x is our variable the entire way. Now we look at the function on the top. What's our function on the top? 2x plus 1. And your function on the bottom is x squared minus 2x plus 1. So therefore, the height is the top minus the bottom. So to find the height, I will take 2x plus 1, and I'll subtract the quantity, x squared minus 2x plus 1. What do I get as I subtract those? Negative x squared plus 4x, and the 1 is gone, right? So that is the height of the rectangle. What's the width? So I multiply by dx. That's the area of one rectangle, but I want how many? Infinite, so I slap on an integral, and now I just need my bounds. How do we, go ahead. You could, and you would have then an indefinite integral, but it will not give you the exact area. We're looking for a numerical result. So I have to find these bounds of intersection. How do you find the intersection between two graphs? You could try your calculator. If you're on the AP exam and they say don't use your calculator, these are both equal to what? Y. And if they're both equal to Y, then they're equal to each other, and we will then find the intersection. If we find where the two functions are equal to each other, that's where they intersect. This is a second degree equation. I'm going to gather everything to the left-hand side. So as I subtract the 2x, I get negative 4x. As I subtract the 1, I get 0. So I factor out an x, and as Luke says, the intersection points are 0 and 4. From my drawing, does it look reasonable that they could be 0 and 4? Yeah, it does. It does. So let's integrate. Antiderivative negative x squared. Plus 2x squared, so it says Patty in the corner. Evaluated at 0 and 4. Notice in this situation, if you plug in 0, you get 0. But if we plug in 4, we do get a result. Negative 64 over 3 plus 32. I'm going to go ahead and find common denominators. If I multiply top and bottom by 3, I get negative 64 over 3, and that will be plus 96 over 3. I get a grand total of 32 over 3. Yep. Very good. So Marissa caught me because I did kind of shorthand this. We plug in 4, and then we plug in 0. Yep, I get it. I get it. You're absolutely right. So as we write that out, that looks more plain now. So that's the general idea. Not that bad, right? Finding the area, so important though, before we move on to things that are more difficult. So let's try this one last one before we get to the other. We'll do this on Tuesday then. It says find the area bounded between the curves y equals sine of x and y equals cosine of x over the interval 0 to pi over 4. Where do you want to start? Graph. I'll draw the graph of sine of x. As Patty said, I'll draw it like this. He even made sounds. He did sh, 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 sh. Okay, like that. I'll even put some marks here. What would that mark be? 2 pi. Pi. So this spot right there would be pi over 2. 3 pi over 2. And then the graph of cosine, how is that different? Yep. And it heads down across that pi over 2 goes to the bottom. Looks something like that. And I'm going from 0 to pi over 4. So I'm starting here and going to that spot. Yeah. And I'm not going to spend a lot of time on this, but some of you might ask, well, how do you know you stop at the intersection? Notice I didn't say find the area between sine and cosine because it kind of bounces back and forth, you know, forever, doesn't it? So I just said from there to there. If you set these equal to each other, just so people can have some confidence here, if we were to solve that equation, I could divide both sides by cosine. And what do you get on the left-hand side? Tangent of x is equal to 1. Where is tangent equal to 1? Pi over 4. Yeah, that's where the sine, that's where the y value and the x value are the same. So we verified that pi over 4 is in fact that intersection point. So, no big deal. What's the top function? Cosine. Minus, what's the bottom function? Times dx, because again, as you were to draw your rectangle, you could see that you have horizontal thickness. And I integrate from what to what? 0 to pi over 4. That's what I'm going to save that. I've decided to save that till Tuesday. So I brought up the vertical thickness piece to just keep it in your brain. You're not going to do any problems today of vertical thickness, but we'll show you that on Tuesday. So we'll spend another day on the area piece. Make sure you're good to go. All right, so it looks complicated, but fortunately, you're really good at trigonometry. What's the antiderivative of cosine? So I have sine of x plus cosine of x. Evaluated at and part of the reason why I include a sine and a cosine is because in the other two problems we saw, if you plug in 0, you just get 0, right? But in this situation, what is the sine of 0? 0. What's the cosine of 0? 1. So you can see that we definitely have to plug in both these values and subtract them. It's not going to, just because you see 0 on the bottom doesn't mean you can just eliminate it. We got to see what happens. So let's plug in pi over 4. We'll draw our little unit circle. Pi over 4 is how many degrees? 45 degrees. And some people see that that coordinate right there for 45 degrees is root of 2 over 2 and root of 2 over 2. Just a reminder, sine is which value, x or y? And cosine is x. So as we evaluate, the sine of pi over 4 is the root of 2 over 2 plus the root of 2 over 2 minus sine of 0 is 0, and the cosine of 0 is, as you said, is 1. The root of 2 over 2 plus the root of 2 over 2 is the square root of 2, and it's minus 1. Please take out your calculator. If I graph sine of x and cosine of x, what are the maximum and minimum values? Right, so if I go into window, I can change my y values to say a -2 and a +2. That will be plenty to be able to see. And then my x values, pi over 4. So if you take pi, which is 3.14, and divide that by 4, everybody see you're going to get a value less than 1. So if I just make this graph a -2 by 2 graph all the way across, I'm definitely going to see this. Should I be working in degrees or radians? Should be working in radians. I'm in degrees because I'm teaching college trig right now. We're doing law of sines and cosines. I press graph. Most people enjoyed that unit. Oh, I'm sorry. Which part? Okay, so mode. Radians. We all good? So I just want to be sure that you guys understand, because people get confused about what the graph means. So I want to be clear about how this works. As I look at the graph, does that somewhat represent what I have shown right here? I mean, does that kind of look reasonable, that region? It does. So that intersection point should be at pi over 4, agreed? So if you wanted to check that intersection, second calculate what? Number 5. You can roam over near this intersection and press enter and enter and enter, and we get 0.785, which should be the same as what? So I check pi over 4, and sure enough, it is 0.785. Now, the last thing I would like to show you is, if you were to try to check your work, okay, I think it was Jaya who said that. No, it was Marissa said you plug in that thingy and you should get that, right? Okay, so let's just see what that looks like then when we plug it in. If I plug in cosine of x and I subtract sine of x, what's interesting here is as you press the graph, it looks different than what we just drew, right? What we are graphing now, it's not the same as this, right? Because we have one graph, not two. What's interesting is, where do you think it crosses the x-axis? Pi over 4. And if you calculate the area, number 7, and go from 0 to pi over 4, pi divided by 4, you should see it just gather that positive area, and we get 0.414. Which should be the same as what? The square root of 2 minus 1. If I take the square root of 2, parentheses, and I subtract 1, you sure do have that same result. Okay? What? Yeah, this piece right here, when you guys get to the test and you go to set up your integral, there's no way to know if your integral is correct. I shouldn't say that. There's no real nice way of doing it. You can represent the problem in multiple ways, but it's rather tedious and challenging. Take out your homework. Let's try to show you the problems that are going to work well for you and those that you should steer away from for right now. Yes? Okay. I think it would be good for you to show up on Tuesday and have worked through problems 1, 2, 5, 6, and 7. Now, as you notice, I've made a little bit of a change over the past couple of years. I have provided for you, especially if you look at problem 5, please look at problem 5. Do you see that the graph is drawn for you? And so I drew the graph, and then I actually shaded it using some yellow highlighter on my computer, so you can see the shaded area that we're working through. So I never used to have those drawn out. So now you can really try to get an idea of what area you're looking for. The bounds are expressed. It says like -1 to 2, but you can see a better picture of that area. So that's piece. However, if you were to look at number 7, 7 does not have the picture drawn for you, does it? So that is one where you will draw it yourself and see if you can come up with those bounds. So both things we need to practice. So we'll finish up area on Monday, or Tuesday, excuse me. You'll be gone on Wednesday, right? A lot of you. And so then Thursday and Friday, we're going to try to get to then volume by discs. But then the week after that will be a little bit of a busy week. So, okay. All right. Yes. Sounds great. We'll see you then.